So we're going to practice the two combination, like circular motion working energy scenarios that I briefly introduced you to in the previous one. One is a swinging type scenario, and the other one is a loop scenario. And again, when something's swinging on a rope or anything, it involves both. If something is in a vertical loop, unless it's going crazy fast where it's like negligible difference in speed, those are the two things that really kick in terms of you got to combine the two together. So we're going to look at a couple just basic scenarios, situations, and sort of how these things can work together. So let's just take something really simple here. Let's say we've got a building over here. All right, and like the sidewalk or whatever it is, something like that. And over here, we're going to have another building like that. All right, and let's color that one in and color that one in. All right, and here we need a line here. There we go. All right, and this, whatever. All right, so let's say this is a bank, and over here we've got a crook who is going to swing across to the bank. Maybe there's an open window or something, doesn't matter. All right, so give him a little rope, something like this, and he is going to swing in. Maybe there's an open window on the second floor that he can actually get into, and then he can rob the bank. Okay, so he's going to swing down there. All right, so let's say that this guy is an 82 kilogram crook, and he's going to swing on down. All right, and we need like the rope. Let's say this rope is 14 meter long rope, and he's going to swing down. The rope isn't starting perfectly horizontal, so let's say he drops down. Let's say that's a 12 meter drop from where he is to where the window is. Okay, so he's going to swing on down, something like that, and we will see how things go here. All right, so what we're going to look for is what's the tension in the rope at the very, very bottom. Okay, so of course tension is forces, but to find the forces I need the speed. So let's look at the speeds a little bit. I'm going to shade on my bank a little bit. There we go, it's a little better. Okay, so I'm going to start with my energy. So at the top he's got potential energy, at the bottom he's got kinetic energy. And I know they're going to be equal to each other. Now of course he's off the ground when he goes into the bank, but I can make this my 0 point if I want to. You can use any reference point you want, and if I want to use the drop of 12 meters, I can use the drop of 12 meters if I want to. I can make that my 0 point right there. So when he's going into the window, yeah, he's got potential energy from the ground, but in reference to the window, he has no potential energy. So I'm going to use that to find out how fast he's going by the window. So of course he's got mgh at the top of the roof, and that's going to take and turn into 1/2 mv squared when he swings into the window, and I'm going to use 12 meters because that's the height that he actually... And I'm getting a little chime of bells from the school. So we're going to use the 12 meter height as the reference, and then we can use that to solve for the v when he goes in. Now, like we've had this before, the m's are going to cancel out because the m's have nothing to do with how fast you fall, and this is a form of falling. But we'll need the mass later on. Okay, so to find out the speed at the bottom of the path, that's just going to end up being 2gh and then square root, and again using the 12 meters as the height. So if I punch that in, we're looking at around, he's going to be at the window about 15.3 meters per second. So that's how fast he's going when he gets to the window at the bottom of the little circular path. All right, so now that I have that, I can work on my tensions. Now, there's a couple forces going on. I'm going to start with just his weight, because, of course, the force of gravity is important. Even if he was just hanging there, there'd be tension on the rope. So if I just do mg for him, it's about 804 newtons. So if he was just hanging there, not doing anything, there'd be 804 newtons of tension on the rope. But he's not just hanging there, he's actually swinging down the rope. And since he's swinging a circular path, this is where your mv squared over r would kick in. So I take that mass, I can take that 82 kilograms and multiply by the speed that I just found, don't forget to square it, and then divide that by the radius of the path. Now the radius of the path is not the 12 meters, that's how far he went. The radius is actually from the rope, and the rope is 14 meters long. So this is going to be 14 meter radius. So make sure you're dividing by the right value. And we will get approximately 1371 newtons for the circular motion. So for the overall tension on the rope, we're going to take those two forces and we're going to add them together because the rope's got to support its weight, plus the rope also has to pull up for the FC. So we will take those two forces and add them together for a total tension of around 2175 newtons altogether. Okay, so you got to use the energies to get the V, and then use the V for the circular motion calculation. And the V is the common thing that often binds the energies and the circular motion type of stuff together. So there's one basic common scenario where both ideas, both the energy stuff as well as circular motion stuff, are required in order to actually solve the question. So let's get rid of this one, and then let's look at the other scenario, which of course is like a vertical loop type setup. Okay, so for scenario number 2, I like roller coasters. Let's use a roller coaster. So I'll try and draw a roller coaster type thing, something like that. There's a loop, and let's say the track came in like that. The track's going to come out like this. There we go. And we'll draw a little roller coaster car. There's a green one. It's upside down. There we go, something like that. And all right, so something like this, guy whipping around in a roller coaster. Okay, so this is a type of situation where we have to use both circular motion and energies to solve what we're going to be looking for. So let's get into some information here. Let's suppose this is just a 55 kilogram guy in the car going around the circle. Let's say it is, let's say it's 18 meters high, something like that. And he's whipping around. And of course, you know, you're going in the loop and stuff like that. You feel pressure on your butt from the seat. There's a normal force. And let's say between him and the car, let's say there's a normal force of 300 newtons. Okay, and of course, if you're in a vertical circle, if you're, the slower that you go, the less force you'll feel from the car pushing you down. So if you're going at minimum speed, you wouldn't actually feel anything between the car. And if some of you have ever been on roller coasters like this, it's really cool because they go really, really slow. And you would actually feel anything on your butt between you and the car. And other carnival rides do this as well. So, but he's going faster than minimum speed, so he's got the car pushing down on him with 300 newtons on his butt. All right, so we're going to find a couple things here. Well, let's the main thing here. Let's find out how fast was he going when he came in the first place. Okay, so we're going to do a couple things here. But first of all, I got the Fn up there of 300. I've also got his mass, so I'm going to find his weight as well because that often comes in handy. So if I do the mg for a guy, I've got the 55 times 9.81. We're looking at a weight of about 540 newtons. All right, so if I go back to our basic vertical circle stuff that we've done, we've got the force of gravity that's going down. This one's also going down because the seat's pushing on him. It's those two things put together which will give me my FC. The same way when we guys did like swinging stuff in vertical circles, it was the gravity and the tension gives you FC. Well, we don't have tension, there's no rope there, but there's Fn pushing him down. So those two put together tells me that my FC must be 840 newtons. And if I know the FC, that's going to be equal to mv squared over r. I can find out how fast he's going. I've got my FC, I've got my mass. The radius is going to be 9 meters, 18 meters high, so 9 meter radius. I can find the speed at the top. So I'll take that 840 and I will then solve for it using mv squared over r and get the speed at the top of the loop. And that gives me about 11.7 meters per second. So just make sure you use the 9 meters as the radius, not the 18. Okay, so now that I've got his speed at the top, again, speed's usually that boundary between energies and forces. I've got the speed at the top, which means now I can find his kinetic energy at the top. So if I find his top EK, doing 1F mv squared, and I'll use this to find out how much kinetic energy he has at the top of the loop. Okay, so if I do that, I can find out that his kinetic energy is around 3,780 joules. Now, of course, he doesn't just have kinetic energy up there, he's also got potential energy. So I can find the top potential energy. So the top potential energy would just be mgh. So I've got his mass 55 times the 9.81. And I'll multiply by the height. So not the 9, but now we're going to use the 18 because that's how far up he is. And his EP is 9712 joules. So now I've got his top EK, I've got his top EP. And if I put those two together, that will give me his total energy altogether. So if I add those two up, his total energy is going to be about, well, we can round off here a little bit, around 13,500 joules. So that's his total energy. So that's my total energy. Now, of course, the total energy never changes in ideal situation. So I can take that total energy and I can move it to the bottom, where at the bottom, it's all kinetic. So this right here, this must be his EK at the bottom. Okay, so if I take that 13,500 and make that equal to 1/2 mv squared, I can solve for the v, and it will give me the v that it must be when he sort of came into the loop in the beginning. Now I know it has to be more than the 11.7 at the top, and if we punch it all out, don't forget to square root, we're looking around 22 meters per second. So he was coming in here at around 22 meters per second. Okay, so there you go. Another example of combining forces and energies together. Again, vertical loop type stuff, really, really common, as well as any type of swinging question. Again, you're often typically using one topic to get to the speed and then using that speed to transition into the other topic.